Hello and welcome to another Big Astronomy Live event. My name is Renee Kerrigan. I'm a member of the Big Astronomy leadership team. If you're not familiar with the Big Astronomy program, this is a National Science Foundation funded grant project that is all about the people it takes to make big science happen. Uh, it includes a planetarium show, which takes you to fantastic telescopes in Chile, and it helps you meet the people who run these telescopes and talk about all the different various types of skills and backgrounds it takes to make big astronomy happen. It also includes a web portal at www.bigastronomy.org that has all sorts of other resources associated with the show. And it has these live events, these ongoing educational events that directly connect you with the people who work in astronomy. And finally, there is research associated with this project, which you have a chance to contribute to after this program today. So today we are exploring the fantastic new Vera Rubin Observatory with Dr. Amanda Bauer, and she'll be speaking in just a moment. But I do want to mention that we have other upcoming events. So we'll have an event featuring Gemini South, which is an incredible telescope at Cerro Pachon, just across the way from the Vera Rubin Observatory, next week on October 27th. And then the very next day, we have an event all about the Cerro Tololo Inter-American Observatory, which is just sort of down one mountain and up another in Chile. So you can learn more about those fantastic observatories by tuning in next week. But now I'd like to welcome and introduce Dr. Amanda Bauer, who is Interim Deputy Director for Operations at the Vera Rubin Observatory, and who will tell us all about this game-changing observatory that is being built. I think construction's finishing up, or, well, she'll tell us all about it in Chile right now. So, Amanda, thank you so much for being here.
Hi, everyone. Thank you so much for having me. I really appreciate everyone joining in and being curious about how astronomy is done and this new Vera C. Rubin telescope and observatory system that we're building. I'm going to go ahead and share my screen so that everyone can see my presentation. Renee, if you give me a thumbs up that you can see that, that would help. Awesome. All right. Here we go. So this is an image of a simulated image of the Vera C. Rubin telescope. As Renee mentioned, we are nearing the end stages of construction of this thing. It was a mere idea about 25 years ago, a little sketch on a napkin, wondering if this kind of system could actually be built. And now we're realizing it. We have about a year and a half left of construction before we start full operations. And so I just really want to tell you today about this. We are honored to have everything named after Vera C. Rubin in January of this year. We used to be called LSST. Maybe some people have heard of that acronym. That doesn't necessarily roll off the tongue, but you'll see me using it throughout the presentation because the Rubin Observatory will produce the Legacy Survey of Space and Time. So a survey is when we look at a lot of the sky and collect information about all the different objects and then present that to different researchers and members of the public around the world. We really try to use Rubin Observatory. Astronomers are infamous for acronizing everything. So we're gonna use Rubin Observatory to really honor her work bringing dark matter to light. She was one of the quintessential researchers who really gave us observational evidence that dark matter did exist, that it did have this gravitational impact. And I'll talk about that a little bit later on and how we're carrying on that legacy. And we're working on a new logo. It's a little bit boring right now, but we'll get there. Very excited about that too. So I want to start with showing you a video. This is in English and it will have English subtitles, but at the link at the bottom, you can go into the YouTube channel and see a Spanish version with Spanish subtitles as well. So I will show you this. It's kind of an overview of what the system is and what types of science we'll be doing with it. The night sky, our window to the universe beyond. Immense, mysterious,
powerful, quietly beautiful. Cosmic events at the edge of our imagination unfold in the darkness, ready to be discovered. When we look at the night sky, we see into the past. Untold stories carried through space by light, the great historian of the cosmos. Technology has evolved over centuries, allowing us to look farther, to the edge of our horizon. We invented telescopes to explore and cameras to capture these traveling messages. Yet the changing cosmos remains unseen. A new telescope opens its eye and captures it all. The objects that move and those that flash, even those we cannot see with our eyes. Every few nights, it covers the sky, finding all that has changed. And within minutes, new glimmers of activity are carried around the Earth to anyone waiting to explore them. What will you discover that no one has seen before? It's time to find out.
Oh, I get goosebumps every time with that one. Okay, let me get back to my presentation. Hopefully. I lost it on here. Huh. Well, I'm not sure where it'll go, so luckily I've got a backup. All right, smooth sailing. Here we are. So what is the Vera C. Rubin Observatory? In the simplest terms, it is the biggest digital camera in the world, suspended above an 8.4 meter mirror with a single image the size of 40 full moons that takes 1,000 pictures of every area of the southern sky over its 10-year survey. This is huge. I mean, big astronomy in every sense of the word. This is a time lapse of the universe that has never been created before. We could never even think about if we have the technology to do this. There are so many aspects that have to work together to make this possible. And the science, the possibilities from solar system discovery to dark energy of what we're actually going to learn with this is just pretty fascinating. So what I'm going to do in this talk is go through kind of each of these lines so that you can see so I can explain to you and you can see what each of these things mean and how they contribute to the possibility of discovery that we have with Rubin. I'll start by telling you where it is. So many of you are familiar with the Coquimbo region in central Chile. We have a base facility that is in La Serena. So we have lots of people, engineers, safety technicians, software developers who live and work in La Serena. And then a handful of folks actually ride the 50 kilometers up into the Elqui Valley every day, up on the dirt road and get up to the LSST site, which, you know, we can wave to Gemini from the top of this peak. And they do the construction work up there. In the top right, you can see the status of the telescope last year. I got to visit. I was very pleased to be able to go see construction happening at that point. And at the bottom right, you can see a modeled version of what the telescope structure itself looks like. Now, right now, in March and April, we shut down construction of the whole facility due to the global pandemic. And we just recently started to open it up. We were able to, following the absolute most safe procedures that we could. So we're just slowly starting to get ourselves back into the construction state, which is exciting. So that 8.4 primary mirror, 8.4 meter, this is the mirror. It took 7 years to build. We introduced an entirely new technology for this that was fabricated at the Mirror Lab at the University of Arizona in Tucson, which is where I'm speaking to you from today. you can see that the mirror has one curved surface, and then on the inside, in the same piece of glass, it has another curved surface, which is something that has never been done before. So it did take a little while. Luckily, they got it right. At the bottom right, you can see me waving farewell to this mirror with its blue protective coating right before we put it in a box and shipped it down to Chile last year. Luckily, it was a successful trip. You can see it exiting the ship in Coquimbo, and then it's the arduous trip through that Puclaro tunnel. You can see the extent. This is the widest tooling or technology that we can send up to the peak because it just barely fits through that tunnel. But luckily, everything went very safely. We got up in the wee hours of morning and transported the mirror. And here's another of my favorite shots of the mirror heading up the mountain, up that dirt road, up to where the Rubin Observatory sits. You can see on a neighboring peak, this is Gemini. So we really are neighbors. We get some great sunrise and sun shots of each other and share those. So the mirror has successfully reached the summit. It's sitting there waiting for the rest of the telescope and the dome to be completed. And very, big mirrors. Big glass is one of the most risky things to move. So we were thrilled that that happened safely. Now this telescope is going to hold the biggest digital camera in the world. It's a 3,200 megapixel camera. It's pretty spectacular. It's been being built at the SLAC laboratory in California. You can see on the left, this is the surface where the image will be collected by CCDs. So you see the nice reflective surface there. This is a model of the entire system together. It's about the size of a van. And then you can see the red and blue massive filters that go in front of that CCD to collect different kinds of light. And so just over the summer, in the recent months, we were able to put the whole thing together after years and years of work being done, cooled it down, and took the first image, so the biggest digital image of the world. And I bet I could take a survey right now and ask you what you think that they took the first biggest digital camera image ever, and no one would get it right. The team had a lot of fun and took an image of a Romanesque broccoli. They built a little light box, kind of a pinhole camera, and projected this onto the surface of the camera and took that image. So the reason they did this was, because it's kind of fun, but also it's just got this gorgeous spiral structure on here. And so if you go to the press release that happened last week, you can sort of zoom in. They have a little web application that you can zoom in and see the structure and see how detailed you can get. But part of this test was to make sure that every single one of these CCDs was working together, that it could collect the light, that they were all oriented the right way. Sometimes your software like flips things around and then you've got this little puzzle. So everything was working. This came out just about a month ago, and we're really excited for this result. The next thing is to finish this off and start its journey down to Chile so we can start to integrate the whole system together. So why do we need the biggest digital camera in the world, aside just from the fact that we can build the biggest digital camera in the world? It doesn't come without challenges. The combination of the Rubin's unique mirror allows the telescope to move really fast, faster than normal telescopes that I've used before. And the camera itself sits right here at the front of the telescope. So what it's going to do over the course of its survey is it's going to look at a part of the night sky for 30 seconds, take an image, move to the next part of the night sky, take an image, move to the next part of the sky. The combination of the design of the telescope and the camera mean that what it can see in a single image covers the area of 40 full moons, which is huge. If you reach your arm out and you put your pinky up, the width of your pinky is one full moon. That's one full moon in the sky, and we're covering 40 of those in a single snapshot. And we're taking one of those every 30 seconds. And so what this is going to do is it's going to cover the entire southern sky visible to the telescope every 3 or 4 nights. So every few nights you get another image and another image and another image, which just is incredible. Like, we didn't know if we could do this, but it's actually working and we're doing it. So the next step, now that we've got the hardware, the physical stuff to make that happen, you need the software. Like, how do you process that many images? It's a lot of data, which I will get into. And then what can you do with the science? So this just opens up so many possibilities. To give you a hint of what this image actually looks like, here is an image from a very well-known survey called the Sloan Digital Sky Survey. It's just one snapshot of a kind of a small part of the sky. This is what we imagine that same part of the sky will look like with the Rubin Observatory. So many more individual objects, so much more detail around. You can see this little triangle of galaxies here that you see in the other image. So many more details of the outskirts of those galaxies. So that's just one teeny tiny part of the sky. Now, let's look at the size of what one single pointing of Rubin will be. You've got a field of view that's 3.6 degrees. That's 60,000 pixels across, a single image. So in order to print out, like say you wanted to print out an image that you just took with this telescope, and you wanted to do it at 72 dots per inch, which is pretty typical, you would need a 70 by 70 foot piece of paper, which is about 20 meters by 20 meters. And then you would have to lay it out on an area that's about the size of 3 tennis courts for one image that we take every 30 seconds. So this, the scale of this, if you're gonna think about big astronomy, this is huge. You can see the size of the full moon and what it looks like across this field. So what do we do with all that? The kinds of science that it might open up, you can imagine when I was a graduate student, what I would do is I'd go sit at a telescope all night and I would point at a distant galaxy. And if I wanted to collect one that's really faint or far away, I'd have to look at it and I'd expose for 20 minutes, 30 minutes. And I would do that over the course of a whole night. And I would add up every one of those photons so I could see detail. But you can imagine if we're looking at this part of the sky 1,000 times again and again and again, in every single one of those images, we can add them together to see fainter and fainter and fainter. But in addition to that, we're going to look at that same part of the sky. Once you look at it once or a few times, you know what it looks like. Then the next time you visit, you can subtract. You can do a little game I do with my daughter where you say, what is the same and what is different? And when you do that, you've noticed things do change. They get brighter, or they get fainter, or they move, or they get more red, or they get more blue, or they appear, or they explode. Like so many things can happen. And no other survey has ever been able to do this over the entire southern sky before. So the amount of things that we will be able to discover, I can't even fathom right now. We can make a pretty good guess at a lot of things, but part of the excitement of big new astronomy is what you discover that you can't even predict you're going to find. In order to do all that though, we need to have some pretty nice solid software. What do you do with this data that comes off the telescope? Every single time we take an image after the first year of observations, we will be doing that what's the same, what's different, but we'll be doing it automatically with the software that's being developed right now by a team of about 100 software developers around the world. You look at the image and it automatically identifies where all the objects are, and it measures things like their positions, their brightness, their size, their shape, and you create this catalog that then goes out to the public. But right when you do, you capture an image and you do the difference imaging, you can automatically understand what's different, and we send out an alert to the entire world right then within a couple minutes of when the observation was taken, every single night. And then everybody can go off and do whatever they want to do once they receive this alert that, oh, something happened. Uniquely to this project, well, kind of fascinatingly, all the code that's being developed is open source and even available now. If you want to see what it looks like, you can go to GitHub and find the project. But what does this mean as far as data? By the end of this survey, we will have collected 40 billion objects that we will have cataloged and measured and made public to everyone. That's more objects than there are humans on Earth. That's the first time any astronomical project has done that before. So what does that actually look like in numbers? We'll collect 20 terabytes of data a night rather. 20 terabytes of data a night that we're moving around the Earth to get into our data facility to process it. In total, that's 15 petabytes in the database at the end of this survey, and all of it will be public. It's public immediately to people in Chile and the US, and then it becomes public over time for everyone. There's a combination of the technology, the hardware, the software, the storage capabilities to be able to make this kind of survey available right now. It hasn't been possible before. So what are we going to do? We're going to do some science. Oh, this little thing doesn't move in my backup safety vision. So imagine in this inset, this image moves across the sky. Apologies for making you use your imagination, but it really does happen. So using that technique, we're going to be able to identify things that move across the sky, mean that they're much closer than the distant stars in the image, because those stars don't move, meaning that it's in the solar system. So we will be taking a census of objects in the solar system. We'll find 5 million asteroids, 300,000 Trojan asteroids that are with the orbit of Jupiter, 100,000 near-Earth objects that have some chance of getting kind of close to the Earth, 40,000 Kuiper Belt objects, which are the things that live way out in the outskirts, kind of out where Pluto is. So many times more of these objects than we know exist now will be found within the first couple years of the Rubin Observatory. One of the interesting things is that the US government had a mandate to NASA to find 90% of all the near-Earth objects that are larger than 140 meters, which is kind of a when they become a real safety issue. And so LSST, this survey, is the only survey capable of delivering that completeness that they specified. So a lot of people are looking forward to this survey. And I wanted to highlight over here at the right, asteroid Bennu. If you have heard about that in the news lately, today, in fact, there will be a little space robot that has been traveling to this asteroid for the last couple of years, and it will go down towards the surface and scoop up a little bit of its dirt and dust and bring it back to Earth in the next few years. So happy day. The relationship to Rubin is that we will be able to detect the targets for this kind of survey, like what kind of asteroid might be interesting, what does its orbit look like? I mean, it takes 7 years to get there and back for this example, so we need to do a lot of planning to figure out which kinds of objects we want to go see. So we will really provide a database for what kinds of objects would we be able to, or would we want to go look at. I'm just going to highlight a couple particular science things that I think are interesting because I don't have enough time to go through all of them. There are, as I mentioned, things I can't even think about or fathom. Mapping our Milky Way. Our Milky Way galaxy is a fascinating example because we are stuck inside of it. We can't get into a rocket ship and go to the outside and turn around and look back. So we're kind of stuck inside our house. How do we know what it looks like from the outside? Well, one of the ways that we do that is we look at all the stars in the sky and we can map out where the stars live, what they look like, what types they are, what colors they are, how old they are, how many times they might have exploded and reformed. And we can do that. You can see on the bottom left, here's an image. And if you try to go deeper, like we can do with our telescope, you can start to see a lot more structure. And so this image on the right here is actually a simulation. You put physics into a computer model and you see what you get out. And so in the future, our observations of where the stars are and what they look like will have to be matched by these simulations and the physics that we input into the simulations to really understand how our galaxy formed. Galaxies are a lot heavier than we thought they were. This was the legacy work that Vera Rubin gave to us. She looked at galaxies and noticed that the stars at the outskirts were moving around much quicker than they should be if gravity that we knew of that was created by all these stars in the galaxy had. And so she made enough observations to imply that there had to be another source of gravity and called that, or implied that that was dark matter that had been talked about for a while, but it hadn't really been seen with telescopes observationally. And so she really created this entire field of study. And that's one thing that we're going to be able to build on, mapping out positions, brightnesses, colors, shapes of billions of galaxies. Looking at where they live, you can see these little cities of galaxies that exist. Each of these dots is an entire galaxy with 100 billion stars in it. Not only can we look at the starlight, but then we can start to infer things about how the gravity is distributed through a technique called gravitational lensing. So now we can look at these dark matter halos that we call them. They're like the houses that people live inside, or each of these galaxies lives inside of this big halo of dark matter. So we can look at that over the entire southern sky and really see how the entire universe was formed using things that produce physical forces, but not light. It's pretty fascinating. So here's just a list of the science themes that we will even touch on. And I'm sure in another 5 years, if I give this talk, there will be new types of astronomy that I can't predict will exist right now, which is the epitome of big science, if you ask me. How do we get to this point creating this? As I mentioned, we are developing technologies that didn't exist before this. And so there's a huge type of a huge variety and diversity of types of people and skills that come into making this project a success. There are optical engineers, there are software engineers, there are safety folks, there are administrators, there are coordinators, people who are doing all the business stuff, in addition to the researchers and the astronomers. One team that I haven't mentioned yet, but I really want to highlight is that Rubin is unique, that among ground-based astronomies, the National Science Foundation invested money in developing an education and public outreach program at the same time that the construction of the big hardware was being built. So this hasn't happened before. And you can see that the team down here earlier this year, we took a photo with the commissioning camera. It's like a little mini, if you can call that mini camera that then got sent down to Chile so we could test out some of the systems. And this team there's graphic designers, there's science writers, there's educators, there's researchers, there's developers. It's such a diverse team, and it's such a fascinating group to work with to create these online experiences that really allow you to have access to the data, context for the data in a way that allows you to explore the universe and be part of the discovery process without having to have an astronomy PhD, because I mean, that's a lot of work. So we have been working really hard to build this program over the last few years. We'll be ready to launch it in the next couple years as the telescope starts to operate and have its data. One of the things that I'm most proud of, I mean, the range of the project, you'll be able to do citizen science project. You'll have activities that will be available in the classroom. They will be in English and Spanish. We've even got a tie specifically to Chilean curriculum so that the educator can use them in their classroom without needing an astronomer. And you can use it with a Chromebook, or you'll be able to use it with the mobile device. Whatever you actually have, you'll be able to do this without downloading data or downloading things for your machine. And so part of this that I'm really excited about are what we're calling these widgets. So we have built these tools that you can use in your browser that allow you to explore the data using, like, how to interact with Instagram, how to interact with Facebook. So these interactions, we're building into these. So in this particular one, if we have time at the end, somebody can ask me, I can show you some live demos. But in this one, we show you different images of a galaxy that has a supernova explode. So you get to find the supernova, and then it helps you calculate the distance to the supernova and the velocity of the galaxy receding from us. And then you get to find that point, and you get to put it on this velocity distance plot. And doing that for several supernovae and galaxies, ultimately, you're calculating the Hubble constant, which tells you how fast the universe is expanding. So by looking, you go from the data, this is what the image looks like, to, wow, the universe is expanding. And here's the distribution of those galaxies in space. So this is one example of this interactive property that we can embed. You can share it with your friends. We can put it with press releases. I'm so excited about this technology, and that the NSF has given us the opportunity to create that. So to round out our time here, we have been on schedule for getting our first light in 2021 and start the full 10-year survey in 2022. At least we were on schedule before COVID hit. So as I mentioned, we've been on a delay since March, and we just recently opened the summit again. So assuming things go well and safely, we will continue to get back into full construction. And so we're expecting a 6 to 12 month delays. We're happy to get through the Chilean winter, and now we're moving into summer. And so with some luck, we will at least reasonably stick to this schedule. And then I am also very excited to release these public education and outreach activities with everyone too. So with that, I will say thank you for your attention, and keep looking out. I'm happy to receive any questions. We're also hiring, so I put a link here if anybody's looking or has friends that are interested. Thank you.
Thank you so much. That was fascinating, and I think everyone can tell that you are passionate about astronomy and the new Rubin Observatory. It's really going to be a game changer. The fact that the data will be available to anyone in the United States and Chile as soon as it is observed, and then even, is it after 1 year, then it's available anywhere?
Yeah, 2 years, and then it's available to everybody. And what we put out through our education and public outreach is available immediately.
It'll really open up opportunities for people all over the world. I'm really excited about that myself as well. We do have some great questions. So there's a few here in the webinar, and there's also some watching on Facebook Live. There's one question from Friedrich Noting the tight fit bringing the mirror through the tunnel, was the tunnel size a size constraint for the size of the mirror?
Yeah, it was definitely one of the size constraints. It turns out, I think it was the Gemini Observatory that I think you'll hear about next week. The tunnel used to be a little bit smaller, and I think they actually worked to widen the telescope so it could fit an 8-meter class mirror through there. Most of the telescopes that we have now are kind of 1 meter, 2 meter, 4 meter, 8 meters, the big one, and the next generation of telescopes will be around 30 meters. So that is absolutely the limit of what the size is of pieces we can get up there. And even the bigger pieces, we have to be able to take apart so that we can fit them through that tunnel.
There's another question from Ralph on Facebook. How sensitive are object positions extracted from these images to temperature changes?
Oh, really good question. One of the things that we're really studying right now is the temperature change from outside into the dome itself where the telescope sits. If there's a temperature difference there, that makes a huge influence on, it's called astrometry, the exact positions of the stars, because that temperature change makes the light bounce around and it essentially makes your star puffier. And so we are monitoring the temperature inside of that dome right now because every little piece of equipment, every little electronic puts out heat. And so we're monitoring, if we put a new piece of equipment in and it raises the temperature, we're like, whoa, back it off, what's happening? So we're really doing everything we can to make sure the temperature inside the dome is the same as the temperature outside. And if it's not, then we have to really work with our software to try to change or, counterbalance those effects as much as we can.
Stephen wants to know, is Rubin Observatory going to be equipped with an adaptive optics system? And how does the air clarity on Serapachone at the Rubin Observatory compare with the Keck telescopes in Hawaii?
Oh, excellent. So I'll start with the second part. The air quality is pretty good over Serapachone. I mean, we are at 9,000 feet, I think, at the top of Serapachone. So you want to get up out of the atmosphere. Mauna Kea is certainly higher than that. It's at about 14,000 feet. So it's pretty high, but we've chosen this site because we wanted to go farther south into the Southern Hemisphere than where Hawaii was. And this up in the Andes was one of the optimal sites to do that. So we're really happy with the air quality of the site. There are issues with increasing light pollution around in La Serena and Coquimbo. So people can find local resources to learn what kinds of lights they can put on outside or turn them off at night to keep that. That's actually one of the biggest influences of noise in our images is the local light pollution around there. I forgot what the first part of the question was.
The first part of the question was about adaptive optics. Will it have adaptive optics?
We do not have adaptive optics. We have something called active optics, which sits on the back of the primary mirror. And so there are little actuators on the back of that glass that can respond to changes in temperature and how the light's coming in. And so they actually change a little bit the surface of the mirror, but not to the degree that they do in adaptive optics.
There's another question here in the webinar. Could you please share a bit more about why the mirror was made with 2 different curvatures and the challenges that creates for the detector?
Oh, yeah, great question. So if we would have had to produce one whole piece of glass for the primary mirror, and then you bounce it off the secondary and it comes down, if you had to put another piece of glass in there, that just adds to the weight and it adds to the size of the whole telescope system. So it becomes much more difficult to move the telescope quickly. So part of reducing the time that it takes to move the telescope around and increase the speed and stability of only having to hold like one big piece of glass as opposed to 2 separate ones, we were able to create this really compact mirror system that could move quickly and take images very rapidly. It doesn't, in fact, affect the camera focal plane because the light that comes only off of that tertiary mirror in the center, it's only that light that comes onto the focal plane of the camera, and that's just one single curvature. So that helps quite a bit. That's similar to any other telescope that's out there. It's just the actual fabrication of having 2 curvatures in one piece of glass was a challenge that we had to figure out with the mirror lab, and they did a really great job.
One person wants to know, how do you know you will catch 90% of the large objects that might hit Earth? I think in reference to the NASA, to the government mandate. And what would it take to find 100%?
I'm not convinced we can do anything at 100%. There's always a little bit of things we don't know, right? So there have been lots of studies at as how many objects are out there. Trying to think of an example. Maybe we go to a beach and you try to, I mean, this is kind of hard to do with your eye, but you try to say, okay, how many white pieces of sand are there? How many pieces of sand are there at this size? How many are at this size? How many are at this size? And so you kind of recognize there are a lot more teeny tiny ones than there are big ones. And so you start to understand what the kind of statistics of those are. And so we've been doing that over the course of history, and we have this little distribution of there are fewer big asteroids, and there are a lot of little tiny dusty things that actually burn up in our atmosphere every day. And so there's a point at the size at which they become dangerous, and that there are enough of them that this government group decided we needed to monitor those at the 90% level, because I can't tell you what's out there in the dark that I can't see, but I could tell you there's likely to be so many houses in my neighborhood. And so that was the statistic they gave. And so if we are starting to get close to detecting, or we can do computer simulations to understand what our sensitivity is and how likely it is for us to detect that size of asteroid compared to how many we think actually exist. Hope that helped.
There's one more question on Facebook from Bo. Could you tell us a little bit about how you change the filters? And is it correct that you have one filter more than can fit on the instrument at any given time?
I'm impressed somebody has done some research. That is absolutely true. There are 6 filters and only 5 fit on the camera at once. So there's this, I don't have it up ready, but there's a really cool video of in the front of the camera, there's like a machine. It's an entire machine called the filter exchanger that was fabricated in France, and it has since moved down. And it's this like arm thing that sort of swaps a filter in and then moves it to the side and picks another one and swaps it in, because the filters are huge. They're like this big. This is a very large piece of glass that has a coating on it of a different color. And so at any given time, there's an algorithm that we are deciding right now for when we have what filter in. One of the 6 filters is called a U filter, which is closer to the ultraviolet. And that would be the filter that we use the least, because when there's any kind of moonlight out, it's not effective. That just totally saturates it. So it can be used less often. So when we have to use that filter, which we have planned, we will know in advance, we will insert that filter for the week that it's on the telescope, and then we will use it more often during that time, and then we will take it back out when we're ready to put the other filters back in. So those would be the more common ones that we use.
There's one more question in the webinar. At the center of our galaxy is obscured by dust, preventing direct observation of the supermassive black hole at the center. Can Vera perform observations to further define the characteristics around the center of the galaxy?
Yeah, what we would do to detect characteristics of that part of the galaxy would be that we would look at the actual stars and see how the stars are moving. And we would try not to look at the wavelengths where the dust really obscures. So we do have a Y filter, which is more into the infrared, so we could see a little bit through the dust that way. And you would watch the positions of the stars change, and you try to contribute to that. We still have to make the final decision of what parts of the sky we're going to look at. And it might be the case that in the end, we're not looking right at the center of the galaxy because of the dust that you mentioned. It might not be that we are the best instrument to be able to do those observations. But there are teams of people who are arguing and doing computer simulations right now to decide whether or not that's the most value that we can get out of our machine.
I have one final question. I was curious if you could tell us a little bit about yourself, how you came to be in this position at the Vera Rubin Observatory, and what inspired you to work in science and astronomy.
Great question. I was a little kid who used to walk to my friend's house and make up my own constellations in the sky. And I was super fascinated by that. I was late to dinner all the time. And right around when I was a teenager, there were 2 really big bright comets in the sky. And I remember just watching those and being fascinated by, like, that's a huge comet that's just hanging out in the sky, millions of light years away. My family were like, yeah, sure, whatever. But it fascinated me. So I ended up going and studying astronomy. I never knew scientists growing up. I didn't think it was a thing you could do. But I found it and studied it and went and got my PhD in astronomy. And then I started moving around the world. And while I was traveling to do research, I was really fascinated by communicating not only my travel experiences with my family, but science to non-specialists. I didn't really like the dry technical writing. I really liked this, like, making people's minds explode by interpreting that kind of stuff. And so I practiced that, and I became more into science communication myself as a scientist and a researcher. And then I started to get opportunities to think about it for organizations, for an observatory in Australia, the Australian Astronomical Observatory. I was there, they appointed me as the head of their outreach group. So I was thinking more at a strategic level about how we could get the message across. And from that opportunity, I got the job as the head of the education and public outreach group for Rubin, which, like, now we've got a budget, now I've got a team, now I can do lots of things. So that was challenging in so many different exciting ways. And then from that, just working within the organization, I had the opportunity to move into a leadership role as the deputy director for operations. And I think part of my strength in that role is the science communication background, being excited about the science itself, but being able to communicate that and have the kind of managerial experience that I've gotten through the outreach roles to be able to, like, how do you operate a multi-$100 million thing and communicate it to the agencies and support all the people who are doing all the work. So it's a really interesting trajectory that I've had moving into this role, and it's been exciting.
Well, thank you so much, Dr. Bauer, for your time. I know that I really enjoyed hearing about the Vera Rubin Observatory and all the different types of jobs it will take to make that observatory work. Because when I was lucky enough to visit Chile first in 2015, it was just like a level. It was just like a level of site. You know, they had just leveled the spot. No construction had started yet. And we heard a presentation about this new telescope and how exciting it would be. And it is really exciting that the construction is close to finishing up, and that we'll have first light before long. And so it was lovely to learn more about it. And we had lots of kudos in the chats as well, people who really enjoyed your presentation and your delivery of that science communication you're very good at, helping people understand about this new observatory. So we really appreciate your time. I'd just like to let our viewers know that there will be an opportunity for you to contribute to the research that's being done on the Big Astronomy project. So there'll be some links put in the Facebook live chat that if you're interested in helping out with that, just look for those links. And again, we have 2 more of these Meet the Observatory programs coming up next week. On October 27th, it'll be Meet Gemini South, and on October 28th, it'll be Meet the Cerro Tololo Inter-American Observatory, CTIO. And then in November, we'll have another Real People Big Astronomy event featuring Dr. Luis Chavara. So thank you everyone for tuning in, and we will see you here again soon in the next Facebook Live event.
Thank you, everyone.